Okay, we're going to be talking about logistic growth or logistic differential equations. Logistic growth takes our basic differential equation, which looks like this. This is our basic equation for general population growth, that the rate of change of population size is proportional to our population size itself. Okay, so, and that's what we talked about when we were talking about our general FAQs and our general population growth. The problem is that this is only accurate for small populations. Small populations do grow exponentially, but the population of New Jersey is not growing exponentially. Otherwise, you guys would not have a place to live. You wouldn't have a school, a seat in a school, because they'd be so overcrowded. The hospitals would be so overcrowded. The population of the United States isn't growing exponentially because that would be ridiculous. The population of the world can't be growing exponentially still because that would be ridiculous. Okay. All environments have something called a carrying capacity, and a carrying capacity is an idea that an environment can only support a certain amount of people. Okay, there's limited resources, there's limited space, there's limited food, there's limited everything. So an environment cannot sustain unlimited population growth. Populations cannot grow exponentially indefinitely. Okay, the relative growth rate will decrease as population size increases. Okay, so the bigger a population gets, the slower it will grow. And then if a population ever meets or exceeds the carrying capacity, then population growth rate will become negative, okay? Because if an environment can't sustain more than a certain number, or more than a certain population size, then it won't sustain that population size. Okay, one of the things that I like to talk about when we get to this section is what happened in China or Japan back decades ago when they were finding that the population sizes were coming way too close to the carrying capacity of the environment. So there were food shortages, there was land shortages, there wasn't enough places for people to live, the hospitals were overcrowded, the morgues and the cemeteries were also overcrowded. That's a gross thing to think about, but it's true. The schools were overcrowded, and I mean the biggest thing was that there just wasn't enough food resources. When that happened, the government stepped in and they imposed restrictions on how many children a family can have, and that worked to decrease the growth rate and brought the population size well under the carrying capacity, and it alleviated a lot of the issues. Now, one of the things that we see decades later, and I know it's become a huge issue in Japan. I'm not as familiar with the situation in China. Not that I'm super familiar with the situation in Japan, but there's been a long-term effect of these laws, and the long-term effect is that population has continued to, well, actually it's continued to decay. Okay, population size, at least 5 years ago, was decreasing in Japan. And they were worried about, now that they imposed new laws to try to encourage families to have larger families, to actually have children. I guess with the laws of only being able to have one child, a lot of Japanese couples were choosing to wait, and then they decided that they didn't actually want children anymore, or whatever such decisions, they decided that they liked their life. And so now there was concern about, or more recently there's been concern about whether or not the population will start to increase again, because if population decays, well, you know what happens. But in any case, so that's like a real world situation of seeing a population approaching its carrying capacity, and in this case, and it's because people are involved. If it was bacteria or animals, they would kind of take care of themselves, but because there were people involved, the government had to get involved and impose restrictions to decrease population size. Because, like I said, if a population approaches or reaches its carrying capacity, you just can't sustain more than you can sustain, so it's a bad situation. Okay, so carrying capacity is the maximum population an environment can sustain, okay, and a big focus on that idea of being able to sustain an environment, okay, a population size. Okay, so therefore, as population size increases, we can better model population growth with a logistic differential equation as opposed to our basic growth differential equation, and that logistic differential equation looks like this, we have dp dt, which is the rate of change of population size with respect to time, is kp, little k times p, times the quantity 1 minus p over k. Okay, let's talk about, there's a lot going on in this equation, so let's talk about what's here. Okay, first I just want to note that this dp dt equals kp, little k times p, is from our original growth formula. And we're actually going to see how this relates to our original growth formula depending on the values of population size and big K. Okay, big P is population size, just like it was with our other differential equation. That little k in there is our growth rate constant, okay, just like it was in our other differential equation. Okay, and note that we use a small k for that growth rate constant. The big K in our problem is our carrying capacity, okay, and that's what's new for this situation, okay. It's a big K that represents carrying capacity and a small k that represents the growth rate constant, okay. Blame the old guys that came up with all this stuff for having two different k's in your equation, a little k and a big K representing two different things. It's in all the textbooks this way, and we cannot avoid it. I want to talk about the logistics of this equation, okay? So let's just start by saying that if population size P is small relative to the carrying capacity, which is our big K, then let's see what happens. Okay, and at this point, if you want to pause the video and try to see what I have my little arrows means approaching, try to see if you can fill in the blanks, and then you can maybe come back to the video and see what's going on. So, okay, so if P is small relative to K, and I'm talking like very small. So let's say the population, or New Jersey can sustain an environment of 1 million people, and I clear everybody out of New Jersey and I put 100 people in, then the value of P over K will be approaching 0. Okay, and then if I have 1 minus a number that's approaching 0, that number will be approaching 1, and that means that this part in here is approaching a value of 1, and dp dt equals kp times 1, which is just kp, okay, which makes this logistic growth equation the same as our regular exponential growth equation. Okay, sorry about that. Hang on for 1 second. Okay, better. Okay, so this makes our logistic growth equation the same as our exponential growth equation. Okay, so we see that if P is very, very small relative to K, then this works essentially the same as our regular exponential growth equation. But for any values of P less than K, I want to talk about what 1 minus P over K is and what that makes dp dt. So what I want you guys to do is pause the video and try to fill in these blanks with either less than or greater than symbols, and then come back to me. Okay, so assuming that you've done that, if P is less than K, then 1 minus P over K will be greater than 0 or less than 0. Well, if P is less than K, I'm going to have a fraction less than 1 in there, and 1 minus P over K will be greater than 0. Okay, and if this part is positive, then the entire thing will also be positive, okay, which means this will mean that population will be growing. Okay, so when our population size is smaller than our carrying capacity, our population will be growing. Okay, and then I want you guys to also fill in the blanks on this one, and pause the video, fill in with less than or greater than. If our population size is greater than our carrying capacity, then 1 minus P over K will be less than 0, and that will make, if this part is less than 0, then the whole thing will be, our growth rate will be less than 0, and that means that our population will decay. Okay, so again, if our population size is less than carrying capacity, population grows. If our population size is greater than carrying capacity, our population decays, and we can also understand algebraically why this happens. Okay, so those are the logistics of the logistic growth model, okay, and let's talk about what you need to be able to do for the AP exam. All that AP has asked you to do with the logistic differential equation in the past is to identify the carrying capacity, okay, the K, and to understand the implications of this value. Okay, anything else that they ask you you can do with your basic knowledge of calculus. Okay, so let's look at a problem. I told you I like bunnies, so let's take our logistic growth equation, dp dt equals kp times 1 minus p over big K, and let's look at this problem. A certain bunny population is initially 100 bunnies. If the growth rate of the bunnies is modeled by the logistic diff EQ, db dt equals 0.2b times 1 minus b over 250, then find the limit as t approaches infinity of b of t. First, let's discuss what this is referring to. If I want the limit as t approaches infinity of b of t, b is my population size, and I want time to go on and on and on. So as time goes on, what's happening to my population size? Well, that's referring to my carrying capacity. Okay, so all they're asking you to do is to identify what the carrying capacity is in this lovely little equation over here. Okay, so what is the carrying capacity in this sweet little equation? Well, as long as I'm in this form, and the big thing about this equation is this 1 here. Okay, as long as I have my 1 minus, that's the right form that I should be in. And I have my 1 minus, which means that this number here is my carrying capacity. So therefore, the limit, as t approaches infinity, of b of t is equal to 250 bunnies. Okay, and that's really all. Okay, so to understand that the limit as time goes on of population size means the carrying capacity, and to be able to identify the carrying capacity in your equation, that's what you need to be able to do for AP. Okay, it's really that easy. Let's look at another one. Okay, so this is a direct problem from the 1998 multiple choice exam, the BC exam. And this is a slight complication on the issue. So the population P of T of a species satisfies the logistic diff EQ, dp dt equals P times 2 minus P over 5,000, where the initial population P of 0 equals 3,000 and T is the time in years. And they asked you, what is the limit as T approaches infinity of P of T? Okay, so one thing that I failed to mention in the beginning is, in the last problem, is that the initial population size doesn't matter, okay? So the bunnies I said that I started at 100 bunnies. I could have started at 50 bunnies. I could have started at 122 bunnies. It wouldn't have mattered because the carrying capacity is the carrying capacity. That depends on the environment, not on your initial population size. Okay, so my initial population size here, again, does not matter. And again, this here is asking me for my carrying capacity. So we said that our carrying capacity is this value, K here, that's in the denominator, that fraction inside those parentheses, so long as this number here is a 1. Okay, this must be a 1. Okay, so our issue with this problem is that I don't have a 1 here, I have a 2 here. So we have to make it a 1. So I'm going to factor out that 2, so I'll have dp dt equals 2p times, and honestly guys, I think it'd be easier to figure out what I should have here that I can multiply back in and get back to my original. So 2 times what would give me 2? 2 times 1 would give me 2. Minus p over, 2 times p over what is going to leave me with p over 5,000? I need a p over 10,000, right? And if I distributed that 2 back in, I would end up with 2 minus p over 5,000. Okay, I think that's the easiest way to think about factoring out, because I know that a couple of you guys, if you paused the video, probably factored out incorrectly and got a 2,500 in there instead of a 10,000. Okay, so once we get that in an accurate way, then all I have to do is identify the fact that that is my carrying capacity, so therefore my limit as t approaches infinity of p of t is 10,000. Okay, here's my last example for you guys. This is again from another actual AP exam. This is from the 2003 multiple choice section. It said that the number of moose in a national park is modeled by the function m that satisfies the logistic diff EQ dm dt equals 0.6m times 1 minus m over 200, where t is the time in years and m of 0 equals 50, and it asks for the limit as t approaches infinity of m of t. Okay, so again, pause the video, come back to me when you're done, and you'll be done in 2 seconds. But this represents the carrying capacity, and this doesn't have a trick to it, so I have my 1 minus here, which means that this is my carrying capacity, so therefore this limit is equal to 200 moose. And that is all, okay? That is really all for our logistic diff EQ. You do your own recap, but I want you to work out tonight when will population size grow fastest, and come to class with a solution tomorrow.